Okay, this is for calculus, our introduction to parametric equations and their plane curves. This is the second video. That's a follow-on to the lesson video with some additional examples. Let's pick up with others examples here. Here's another one. Graph the plane curve and write the corresponding rectangular equations for this set of parametric equations. All right. So here we've got cosine and sine of 2 theta. We can't directly use the Pythagorean identity here as is, because that requires that we have cosine squared plus sine squared of the same thing. But I could actually do this. I'll do this part first to see if it helps in sketching. I don't think it will in this case, but we're directed to find it, so we will. Let's see. I'm going to do, there's a trig identity that says that sine of 2 theta is equal to 2 times the sine of theta times the cosine of theta. So that's actually, we're going to make this that. That means y is equal to 2 times that, which means we've got x is cosine theta, but y is really 2 times 2, so it's 4 times sine theta times cosine theta, right? And then how can we combine those? Well, I'm thinking, let's see. What if I were to do this? I've got sine, I've got cosine here. X is just cosine. If I could write y in terms of just cosines, then I could replace those cosines with x's. So what I'm going to do is, it's not going to seem intuitive, but I'm going to square both sides. If I square both sides, I get y squared, and over here I've got 16 times sine squared of theta times cosine squared of theta. And then that means that I can replace the cosines here. Each of these cosines is really an x, which means I get to replace this and say this is y squared is 16 times sine squared of theta times x squared, because each of those cosines is an x. Okay, now I still have some sine squareds here, but I do know that that sine squareds are equal to 1 minus cosine squareds. So I could expand this into 1 minus cosine squareds, right, along with my 16 and x squared that's currently there, and then replace those also with those cosines with x's, because each cosine is an x. So that's x squared times x squared. Okay, at this stage, we have converted this to a rectangular form. That does not look in any way like anything that's easy to graph. So I've done what they said, write it in rectangular equation form. If I wanted to try to solve it for y, it would be plus or minus the square root of that. I don't think this helps me in graphing, right? So it was an interesting thing to do, required knowing a trig identity to even do it. So in this instance, instead to graph it, I'm just going to resort to a table. So let's say make a table with t, x, and y, and then we'll pick various values here to plug into the original. I'm just going to go back to working with the original set here. Right, so 0 is convenient. Cosine, oh, this said 0. That's actually theta, the parameter is theta. Okay, so if I plug 0 in, the cosine of 0 is 1 from our unit circle, right? And here if I plug in 0, I would have sine of 0, which is 0 times 2, so that's 0. So that means I could start graphing this. Let's make some tick marks here. 1, 2, 1, 2, 1, 2, 1, 2. And our first point, we're at 1, 0, and that is when theta is 0. The parameter is theta is 0. All right, we'll do some more points. Another convenient point would be, well, let's do something maybe like pi over 4. So this would be cosine of pi over 4, which would be the square root of 2 over 2. This would be 2 times sine of double that. So this would be sine of pi over 2. Sine of pi over 2 is 1 times 2, so that's 2. And square root of 2 over 2 is about 1.4. So if I want x is, let's see, x is 1 point, wait a second, 1 point, no, it's not 1.4, it's half of that. So square root of 2 is 1.4, so half of it's about 0.7. So 0.72 would put that up here. So we're here at theta is pi over 4. Okay. Another convenient place would be pi over 2. So cosine of pi over 2 is 0. And if I double that, that would be pi. Sine of pi is 0. So this would also be 0. So that means we're at 0, 0 at theta is pi over 2. And that suggests that the path looks kind of like this in this direction. Okay, so if we kept doing this, the next one would be 3 pi over 4. And then the x would be the cosine of that, which would be negative square root of 2 over 2. Right? And then sine would be, let's see, 3 pi over 4 doubled would be where? Here's 3 pi over 4. So if I double that, that's 6 pi over 4, which is 3 pi over 2. So sine would be 1, right? And that would be times 2, sorry, negative 1 times 2. So this will be negative 2, actually. So we would be at this location at negative 0.7, negative 2, when theta equals 3 pi over 4. Right, so you could laboriously do all this by hand, and you'll end up sketching out this shape. It looks like a bow tie, actually. So I don't want to take too much time to do it, but it's very tedious. You could do this by hand and get this shape here. All right, so that's what we would have to do. Now, this would be much easier if you're allowed to use a calculator. If you can use a calculator, then you could just put that calculator in parametric mode, so PAR, go here to y equals, and enter the equations for x and y in terms of the parameter. So x is going to be cosine of the parameter. It's going to show up as a t here, but we understand that that is a theta. And then 2 times sine of 2 times the parameter. And if I graph that, zoom 6 is origin plus or minus 10, and 0 to 2 pi. I can see that it's tracing out that same thing. Let's see, I can actually make this a little smaller, like negative 3 to 3 maybe, just so I can see it more clearly. I'm changing the limits for x and y to negative 3 to 3 so we can see that bow tie shape better. All right. And the parameter region that requires that, what does that? So right now this by default comes up to 0 to 2 pi. What if I just did from 0 to pi? How much of the curve would that show? That actually shows that much of it. So it does require to go all the way from 0 to 2 pi if we want to, for the parameter range, in order to see the entire curve once. Okay, so there's the first additional example. Let's do another one. Graph this plane curve and write the corresponding rectangular curves now, or equations. Now in this one, I think we can do this one without a calculator pretty quickly, because I've got sines and cosines of just theta. Right, so what I'm going to do is solve, let's go to corresponding rectangular equation. If I solve this for theta, 3 times cosine theta is equal to, let's see, x plus 2, if I move that 2 to the other side. And then, let's see, that makes cosine of theta equal to x plus 2 over 3. The second equation here, if I solve that for sine, 3 times sine theta would be y plus 5. So sine theta is y plus 5 over 3. And since cosine squared of theta plus sine squared of theta has to equal 1, that means x plus 2 over 3 squared plus y plus 5 over 3 squared has to equal 1, which means x plus 2 squared over 9 plus y plus 5 squared over 9 equals 1. If you multiply by 9, we would get x plus 2 squared plus y plus 5 squared equals 9, and that is the equation of a circle centered at -2, -5. So I can graph that quickly, much quicker than with the table. It's going to have, let's see, the center at -2, -1, 2, 3, 4, 5. And then the radius is 3, because 9 is 3 squared. So we'd go back there and draw something like this. Okay, the only thing is, I do have to know the direction. So I'm going to have to make a little piece of a table. So t, actually it's theta, x and y. Let's pick 2 convenient points. How about 0 and pi over 2? If I plug 0 into the x here, that would be negative 2 plus 3 times cosine of 0, which is 1, so that would be a 1. X is 1, and y would be negative 5 plus 3 times sine of 0 is 0, so that's negative 5. So we're at the point positive 1, negative 5. That's right here on the curve at theta is 0. Okay, and then if I go to pi over 2, right, this is going to become, let's see, negative 2 plus 3 times the cosine of pi over 2, which is 0. So this is negative 2. And the y would be negative 5 plus 3 times sine of pi over 2, which is 1. So that would be negative 2. So we would be at negative 2, negative 2. So right here at theta is pi over 2, which means our direction arrows will go that way. So we'll go counterclockwise around this circle. All right, another really good example, typical example. How many more do we have? 1, 2, 2 more. Okay, so this one says write the corresponding equations, draw the plane curve. I have cubes here. I don't think this is going to be as pretty. But let's go ahead and try to write it in the rectangular equation form and see if it assists us in graphing. So I can take one of these and solve for t, like maybe the x equation. If we take the cube root of both sides, cosine of t would equal the cube root of x, right? Yeah. And then I could actually do the sine as well. Sine of t would equal the cube root of y. And then I could use the idea that cosine squared plus sine squared has to be 1. That's the Pythagorean identity. So I would have the cube root of x squared plus the cube root of y squared has to equal 1, which just tells me x to the 2/3 power plus y to the 2/3 power equals 1. So this is the rectangular form, or so is this one. But it doesn't really help me in graphing. So I think I'm going to have to go back to a table. So let's see, the parameter is t, x and y. We'll pick some values here. Since we have trig functions, maybe we'll do 0. So cosine of 0 is 1. 1 cubed is 1. Sine of 0 is 0, so that's 0 when we cube that. So that means we're going to start at, let's see, how big should I make this? Probably pretty zoomed in. This is going to be at 1, 0 at t equals 0. Okay, then we could pick maybe pi over, actually let me try a lot of granularity here. What's pi over 6? So this would be, let's see, cosine of pi over 6. Cosine is square root of 3 over 2, but then cubed. So that would be 3 times the square root of 3 over 8. Wow, okay, so yeah, 3 square root of 3 over 8. I think we need to have these numbers in decimal. So I'm kind of resorting to a calculator anyway. This would be hard to do without a calculator, but so let me just do that. Let's just take the cosine of pi over 6 and then cube that number. In decimal, that's 0.65. I'm just going to write the decimal numbers here. So decimal number will be 0.65. And then the sine cubed, so if I took sine of pi over 6, I'm just doing this quickly on the side calculator, pi divided by 6, and then cube that number, I'm getting 0.125. So that is, let's see, where is that going to be? 0.65, 0.125 is around here, and that's when t is pi over 6. Okay, and if I were to do pi over 4, same color scheme, pi over 4. Cosine of pi over 4 is the square root of 2 over 2. Cosine pi over 4, and then if I cube that number, I get 0.35. If I take sine, it's actually the same, so 0.35, 0.35. 0.35, 0.35 would be roughly here when t is pi over 4. And when t is pi over 3, cosine, actually it's going to be the sine and cosine in reverse. So this will be the 0.125, And this will be the 0.65. That means this is 0.125.65 when t is pi over 3. And then when we're at pi over 2, this will be 0 and 1, actually. So the curve looks like this, and like that, in this direction. And if you continue with this table, you'll end up getting a shape that looks like this. Okay, and you could verify that, of course, in your calculator. You would just enter these equations, if you're allowed the technology, on that part of the test. You can go and make this, let's see, parentheses, cosine of the variable, but cube that number. And then same thing here, parentheses, but the sine of the variable, but cube that number. And if I do zoom 6, and zoom quite a bit in there, so let's just go max from -2 to 2 in x and y. Sure enough, it gives me that kind of rounded diamond shape like that. All right. Let's take a look at the last example. The last example says find two different sets of parametric equations for this normal rectangular function. Okay, so the most common way to parameterize is just to make one of the variables the parameter. So x could be t, and therefore y would be, let's see, that x squared, we just take that and replace the x with t, so t cubed. That would be a parameterization. We could certainly do that. Or, I don't see any real other obvious, there's not like a function inside of another function, so what if we made the y variable the t? Then that means x would be the cube root of t. Right? Each of these are valid parameterizations. Well, that was quick. All right, and I think that is the last example we have. So that should hopefully help you out as you set out to do your practice.